Good evening and welcome to Delivering Elastic Data Pipelines with Michael Hausenblas. My name is Henrietta and I work on the community team here at eSynergy Solutions. eSynergy specialises in open source and cloud resourcing. If you're looking for a new opportunity, we can help you find the right role tailored to your skills and experience on either a contract or permanent basis. So please send over your updated CV. Should you be looking to build out your team, we can help you with hiring and attracting top talent. Alongside this, we can also help you with upskilling your employees around the latest open source and cloud technologies. Now, moving on to some housekeeping. If you have any questions for Michael, please fire them over via the question box throughout, and Michael will answer them at the end of his talk. We are recording the session, and the slides and recording will be made available and sent to you tomorrow by email, along with my contact details. Now, I'm going to pass you over to Michael to begin his talk.
All right, thanks a lot for having me, and pleasure to talk about elastic data pipelines in the coming hour. And for the end, I have at an enormous rate. So if you look at a single flight, generating gigabytes of data. If you are able here in this case to increase the accuracy of the ETA, of the expected time of arrival, only for like 50 minutes or so, you to generate a lot of money, millions potentially over a year for a single airline. Take the logistics. If you're shipping containers, in that case, a little hint of what's coming up in the future. Again, data is generated on the flight and needs to be processed on the flight. The same is for healthcare. So IoT, you've got a lot of devices there, and the faster you react, the more likely it is that you, at the end of the day, save lives. Right? And cities, smart cities, where you have tons of cars and buses and whatnot, and you want to optimize the flow there and so on. Again, always this same pattern. The data is generated and needs to be processed on the fly, and that means that the overall load is rather unpredictable. There might be peaks, and while it's by and large possible to come up with an estimation, it's not always that easy, and you have to think about the resources you put in there. So you typically provision for peak load, but most of the time then that means that your resources will be underutilized. Last but not least, yourself. If you think about no matter if it's a smart watch or anything in your house, anything that produces data there, again, you want to be able to process that and take actions as the data arrives. So in the first part, I hope that we've motivated why we're doing that, why we need that. I've put together what I call a tool belt or toolbox that essentially lists the components that myself and others typically use in this setup and to realize a data pipeline. So let's first talk about a bit of what different kinds of workloads we see. There are obviously batch-oriented workloads, be it Kronos in the Mesos world or Hadoop. There are batch streaming systems, Spark, Flink, and then more to the real-time aspect, low latency Storm and Samza. And then there are PAS level frameworks like Marathon, Kubernetes, and typically in a real-world setup, you have a combination of all of them. You have some batch-oriented, some low latency interactive, some streaming, and you want to be able to cover all of them at the end of the day. So the first part of the toolbox talks about message queues and routers. So as the data comes in, you typically need to queue it, and there are plenty of open source components, open source technologies, including Kafka, Fluentd, and others that allow you to do that. And there's actually Also, public cloud providers typically offer their SES-based solutions. And there is a very nice website called Qs.io that lists and discusses all of them. And I will just have a closer look into two. One is Kafka, and later on in the demo I'm going to show you something around Kafka. Essentially, the LinkedIn guys had to introduce that because they had a couple of producers and a couple of consumers, and to avoid these hard dependencies and hard wiring between them, having this message system in between where the consumers subscribe, publish something, and producers can subscribe to certain topics and read them out, and the messages don't go away immediately, but as long as a producer wants to, consumer wants to read from the queue, they stay around. It's hugely popular, and in the meantime also a commercial entity called Confluent is behind that. Fluentd is a bit of a different kind of system, has a bit more routing, pattern matching in there, but essentially the same idea, so you decouple producers and consumers. Second, talking about stream processing platforms, and you've got the usual suspects, as already mentioned earlier on, Storm for low latency, Spark, kind of hybrid, both batch and stream processing possible, Samza, Flink, there is Concord, and again, you will find respective stream processing platforms or hybrid platforms in the cloud-only area. And I did a webinar on that if you want to look that up. So talking about Storm a bit, it's definitely battle-proof and has a lot of community and a lot of advantages. It is probably the oldest open source stream processing platform I'm aware of, and is in production quite widely used. And really, you want to use that if you have a low latency requirements. You want to process the data in milliseconds or less, and also scales quite well. Spark is a bit different in the sense of that, as I said, you can combine the batch and the stream processing part. It's agnostic to the storage layer, so you can read and write from two different kinds of data stores and file systems, and the streaming is kind of a micro batch, really. So it's not necessarily useful for low latency, if milliseconds or whatever. A second or two is no problem, but I would not necessarily use it for milliseconds. That's not really suitable for that. The big advantage is, though, that you can realize things like the Lambda architecture with it, because it allows to do both the batch and the stream part, and it offers a couple of different APIs, interfaces, such as SQL and machine learning and graph processing and so on. So you have a kind of unified processing platform with that. Last but not least, talking about time series data stores, quite often you will be dealing with kind of events and time series, timestamps. There are a couple of solutions out there. Again, a number of open source platforms, including Influx, OpenTSDB, KairosDB, which is a port of OpenTSDB on Cassandra, Prometheus, and I've listed another few on the IOTA info webpage there. Talking about OpenTSDB a bit, this is really something you want to use for large-scale time series processing. So you're talking about billions of data points and so on. Sits on top of HBase and respectively is very, very scalable. It might be a bit, too much for smaller deployments, so that's why I also listed InfluxDB here, which really a powerful query language. It's SQL-like, so it's very easy to intuitively get a feeling for the time series that are in there. And yeah, it's written in Go, so there are no external dependencies. You just have a single way in Docker, very, very straightforward to operate and connect with things like Grafana, for example. So looking at that Toolbox, there are obviously a couple of challenges that come with that. First observation is distributed systems are hard. So let's not fool ourselves. Writing or extending or using things like Cassandra and Kafka and so on requires a bit of knowledge and experience, and quite often you just want to use these things without really digging into the theory of distributed systems. So this is something we don't want to hide or pretend it doesn't exist, but we can make things easier, I believe. Second thing that I can tell from my own experience, it's really quite cumbersome to really set up and operate these, especially distributed systems, properly and make sure everything keeps running and you can extend them and make them available to the development team. One consequence of having a multitude of different components, for example, if you combine Kafka with Cassandra and Spark, is that you end up having static provision clusters per component. So one component, for example, being a distributed database like Cassandra, and another one, Spark, is an example of a distributed query or processing engine. And that obviously means you have fixed sized clusters, and it's rather hard to adapt to the business requirements if you need more Kafka nodes or more Cassandra nodes or whatever. And as a consequence of that, you typically also see very low cluster utilization. So industry standard being around between 10 and 15%. That's one of the challenges that you typically deal with. The question is, can you make that better? Can you make it easier for people to set up and operate these components, have a higher cluster utilization, overall cluster utilization, and with that a better TCO? So I'm going to suggest now something, or introduce you to something that I believe has the potential to solve that, and that is the data center operating system. The basic idea behind that is having a resource manager, a distributed resource manager. In our case, it's Apache Mesos, and this resource manager essentially takes care of pretty much the same thing as you have in your Linux kernel, abstracting away all the resources, CPU shares, RAM, disk, port, whatnot, and make that available to what we call frameworks that you see in the uppermost layer there. And frameworks can really be anything. So if you have a Java application or Python or whatever, you might use Marathon or Kubernetes to launch that. If you have a database or Spark or whatever, then there are frameworks Mesos frameworks that either ourselves or together with partners or someone out there has written a framework to make a certain distributed system work on top of Mesos. And that means essentially that it's really super easy for you to use these different frameworks together in an application. And as you can see in the lowest level, it runs on any kind of infrastructure. So you can run it on bare metal, you can run it on VMs, you can run it in the private clouds, think OpenStack or whatever, and you can obviously run it also on public cloud providers. And to sum up, so this DCOS, the Data Center Operating System, is a distributed operating system with Mesos as its kernel, and then you have a number of services and applications that all benefit from the resource abstraction and the set of common operations and services that Mesos exposes. So what are the benefits of DCOS? On the one hand, it allows you to run stateless services. Think about a web server, Nginx, application server, Node.js, or whatever, together with all these big data services like Kafka, Spark, Cassandra, and so on and so forth on one cluster. That means that rather than having to upfront partition your racks or whatever you're using, and say, okay, these 5 machines, they are for the Kafka cluster, and these 10 machines are for Spark, and so on and so forth. What DCOS does, it allows you to dynamically partition and provide each of the frameworks and applications with the resources it needs, or as it is dictated by business requirements. For example, you say during the day, 80% of the resources should go to the web servers, and at night you dedicate more resources to your analytics that runs on Kafka, Spark, and Cassandra, for example. And because you have these different frameworks running all on top of the same cluster, you typically have a really huge increase in utilization. So we have seen 80% or more resource utilization in DCOS Mesos clusters. One thing we're trying to do is addressing particular things, like in our case, data pipelines with a specific opinionated set of frameworks and services together. In this case, it's Infinity, and Infinity essentially gives you all these different selected bits and pieces out of the toolbox to realize a very agile and flexible data processing pipeline. It's using Kafka, Cassandra, Spark, and Docker, and the underlying resource management, as I said, is Mesos. And in the following, I'm going to show you a bit more in a concrete example of how the whole thing works. So I picked 2 examples as a kind of overview, and then one hands-on example where we actually will see the DCOS in action. The first one is a very simple data pipeline, simple because there's only one path. I assume that you're familiar with GitHub, and you might also know that there is a API where you can gather all the kinds of events that happen within an organization. So let's say the organization is ourselves, Mesosphere, and then people would commit and create issues and comment and so on and so forth. And all of these events are available as JSON from API, GitHub.com, orgs, and then the org handles, so Mesosphere in our case, and events. And I have a little GitHub fetcher there that essentially pulls that JSON and stuffs it on into KairosDB, which is time series database. I mentioned a port from OpenTSDB on Cassandra, and with Cassandra we have this very, very scalable and flexible database where you can stuff in millions and billions of events. The whole thing is launched through Marathon, which is essentially a bit like an init system for a distributed system such as the DCOS. And once the data flows in there, it is eventually processed and displayed in Grafana so that you can actually see these time series in action and compare them. And if you want to, you can go to that GitHub repository, github.com, Mesosphere, Cassandra, KairosDB tutorial, and try it out yourself. You will see only a few steps, and it's pretty straightforward to do that and to adapt it to your own needs. You can, for example, use a different data source or use a different visualization at the end, rather Grafana something else, for example. A slightly more complex data pipeline, example of a data pipeline, is the time series DCOS demo we did end of last year. And I've just referenced the blog post because it explains a bit more of the context, and from there also the GitHub repository, the underlying GitHub repository is available, so you can again try it out yourself if you want. And there you see both Kafka and Spark working together, feeding essentially 2 different paths. One is the online path, the other one is the offline path. And what we did there is essentially we took crime data from the open data portal in the US, and that essentially uses crime statistics in the Chicago area. and then turned this dump into a stream, essentially going through that line by line CSV dump, and then spitting out one event after the other, and each of the events has a timestamp and a latitude and longitude, and that is published into Kafka, and then Spark reads it out. So Spark streaming job that reads it out. On the one hand, writes it into InfluxDB, so that's the time series database that's then plotted, and then on the other hand, it's aggregated, and essentially different kinds of crimes are aggregated in terms of their location, and that is through a fetcher made available in an Nginx Docker container that uses a heat map to actually show where are certain hotspots of crimes. And the whole, again, is launched through, on the one hand, Marathon, on the other hand, we're using Kubernetes here, just to show the flexibility as well. We could have done everything in Marathon, for example, but we wanted to show different ways of launching things like a fetcher or InfluxDB or Nginx or whatever. And now it's time for some hands-on, and just give you a bit of heads up what's going to happen there. I'm going to install Kafka. I'm going to start a Kafka broker, and then I'm going to use a little utility called Kafka Cat to publish and consume topics online now. Let's see if that works. So what you see here is a DCOS cluster. I have 6 nodes here, and overall I have 24 CPU shares and 82 gigs of RAM. And Marathon, the system Marathon, as I said, it's kind of the init system, is already running. It's running per default, no tasks there yet. And the first thing, as I said, that I want to do is to install Kafka. So let's install Kafka. DCOS comes with a command line interface, and that's what I've installed here. So every DCOS command starts with DCOS, and then in this case, this is the kind of package manager if you want. It lets you install and list and so on all different kinds of services. So Kafka is now being installed. We can actually have a look what's happening there through Marathon. As I mentioned, Kafka is launched, and we can see what happens there. So essentially, Mesos, as I said, the underlying resource manager, takes Kafka and installs it on a couple of nodes, and at some point in time, now we see the Kafka service as such is available. If we look into that, you can see that it's idle there. There's nothing pending there. We can have a closer look at that, how exactly the configuration looks like using Marathon. So if we look into that, that's the configuration it's using. Launching this Kafka, providing the zookeeper URL, a couple of health checks there, a couple of other things that we need as prerequisites to run Kafka, and now everything is essentially ready to rock. The next thing I want to do is I want to add a broker, a Kafka broker. So we've started the broker now, and I'm going to note down this endpoint because I'm going to need that for the Kafka Cat. So the first thing I'm going to do is I'm going to launch that. So let's just check if everything is fine, if I can actually have an access there. And yeah, Kafka Cat, as I said, that's the Docker container Docker image that allows me to interact with the Kafka broker. And now what I'm going to do is I'm going to open up a second one here. And again, launching on the one hand, simulating a producer on the left-hand side. That's the -p flag here. And on the right-hand side, I'm going to do the same thing as a consumer. So what I would expect now is if I'm publishing topics here, so if I, let's assume I'm whatever data source there, and I hit enter, then I should see that on the right-hand side, and indeed that's what's happening, right? So each of these lines represents essentially one message in the topic called test topic here, and that's the publisher on the left-hand side, and on the right-hand side I have launched Kafka Cat as the consumer mode, so it will listen and read from that test topic, and whenever it has it, sees a new message, it will echo it to standard out. That's what's happening there. Okay, so that was the little demo, just to summarize what we've been doing there. Essentially, within a few minutes, and if you take away the network issues we had, it was really just a few minutes. We have installed Kafka, we have launched the broker, and using Kafka Cat essentially started this publishing and subscribe consumer cycle as a whole. Okay, and that was pretty much all I wanted to show you for now. And now I'm looking forward to questions. How do you ensure the cloud frameworks you offer are secure? So just in terms of terminology, so the first question, how do you ensure the cloud frameworks you offer are secure? On the one hand, it's not necessarily a cloud framework. You can run Mesos and DCOS in a public cloud, but you can also run them in your private data center. And depending on what the underlying infrastructure gives you, you will have different ways to secure your overall system. So for example, in AWS you have security groups. So the 6 nodes that I've shown you here, 5 of them are so-called private worker nodes, so they're not reachable by any means from outside of the cluster, and with 1 public node configured that, in my case, is available from 0.0.0.0, so from everywhere, but you can also lock that down and say only available from that IP range or whatever. Then you typically want to also lock down the access to certain frameworks. So you could, for example, say my system administrator has obviously access to everything, so to Marathon and to Cassandra and so on, can install new services like Kafka and so on. But this user group only has access to, let's say, a certain application or a certain framework. So someone in research might only have access to Spark together with Zeppelin for interactive analysis using Spark. Obviously you also want to integrate with your existing authentication and authorization frameworks. So, for example, you want to use, I don't know, your existing Active Directory LDAP infrastructure and want to, reuse these users and user groups and provide access based on the existing structure that you find in your environment. And again, if you don't have that, then typically your underlying infrastructure, cloud provider, whatever, gives you the primitives that you need to lock down access or provide access control. The second question we have here is how many frameworks were used in this example. I'm not entirely sure what you mean by this example. I've shown 3 examples. In the first one, I believe there was only one framework, so the Cassandra framework, and Marathon, but again, as I said, Marathon has a special position in DCOS. It's launched by default and used as a launchpad for all the other frameworks, long-running frameworks such as Cassandra. In the second example, we have 2 frameworks, HANA and so on, are essentially all Docker containers, Docker images that are launched through Marathon and Kubernetes respectively. And in the third case, the Handson example was Kafka only, so one. Third question we have here, how to make sure the one Mesos framework will not overstep another framework. Yeah, so that's something that's built into Mesos itself. Mesos is what is called a 2-level scheduler. So Mesos essentially only offers the resources to the different frameworks, and then depending on pending tasks. So, for example, Spark might, there might be 3 users submitting 3 batch jobs, for example. The frameworks, it's the responsibility of the frameworks then to accept these offers. So, for example, Spark might say, 2 CPU or 10 CPU shares and 10 gigs of RAM and whatnot. And if these resources are available in the cluster, then Spark can take these resources and actually makes the scheduling decision itself. So that's the principle with Mesos, that's what's called a 2-level scheduler. If you think about that Mesos itself only abstracts the resources and offers the resources to the frameworks, and then it's part of the responsibility of the framework, which consists of a framework scheduler that has the logic how to deal with the resources. So, for example, Marathon is for long-running tasks. So the idea there is once one of the tasks or applications, that's the Marathon terminology, stops, Marathon will restart it, because the assumption is it is a long-running thing. So at the end of the day, if you don't have a while loop in there, and I see that sometimes that on Stack Overflow that people are surprised by that, then Marathon will keep restarting your things. So it is really a combination of the Mesos core working together with the frameworks and Mesos guaranteeing a fair resource sharing amongst the frameworks that yields the answer here. One more question. What was used to get CPU RAM usage feedback into Mesos framework? So I'm not entirely sure if I interpret your question correctly. If I don't, then please come up with a follow-up question. What happens essentially is that on each of these nodes, so let's go back to that one here, you have a cluster of machines, and in each of these nodes there is a Mesos agent running, and Mesos master, which is the kind of brain of Mesos, and it's typically not only one master, but there are a couple of masters coordinated through Zookeeper, will get reports from the Mesos agents that sits on each of the nodes, whereas a node, as I said, could be a virtual machine, could be bare metal or whatever, and they essentially it is configurable, so you can tell them, only report half of the CPU available or half of the RAM or whatever. If you don't provide anything, then the Mesos agent will make an educated guess. But it's responsibility of the Mesos agent to report the master and say, hey, here on my box I have so and so many CPU shares and RAM and so on available, and then Mesos takes that across the entire cluster and makes these resource offers to respective frameworks. How scale down is implemented to make sure Marathon task was completed before it's killed? How it's done for Cassandra node as example. So So for the first part, as I said, Marathon is for long-running tasks. So if you have a one-off thing, like you want to have, I don't know, like a cron job, you would use Chronos for that, or you would use the Mesos, just a simple framework for a one-shot. Marathon assumes, it's the logic of Marathon to keep your task running. So even if you don't have a while loop in there, implicit while loop, then Marathon will notice, oh, that application is not running, and then restart it again. So there is nothing unless someone says, let's kill that application explicitly, unless the user explicitly says, stop, I don't know, in our case, I don't know, InfluxDB or whatever. Marathon will keep it running. In case of Cassandra, it's really the responsibility of the framework itself. So if you take Cassandra, then people have been writing Cassandra for quite some years now. There's also commercial entity data stacks behind on. And what the framework really does is it provides, again, remember, a framework consists of a scheduler and the executors and tasks on each of the agent. It kind of leads between the resource offers, Mesos master gives, and what the respective framework needs. So from an operational point of view, you do whatever you do with a normal Cassandra cluster. It's just that you can install Cassandra, multiple versions of Cassandra, run them in parallel, and are very flexible in terms of how many resources you give it. And at the end of the day, it boils down to, again, if we look at how Kafka is set up, so each of the configurations, it lives in a certain GitHub repository here. That's what's behind there. And if you look at the log, that's exactly what you would expect there. In terms of what the framework really does, or we can also look at the configuration of Kafka, and again the same applies to Cassandra. What is actually happening in the background? So what happens if you say ECS package install Kafka is that we have a pre-configured repository which lives under the so-called universe or multiverse GitHub repository that has all these commands in there, and you can adapt that and change things like how many CPUs or on which nodes and so on and so forth. But that's essentially what Marathon then uses through Mesos to launch that. So all of whatever is happening inside of Kafka in that case, that is really up to Kafka. So we don't really change any logic or whatever of these frameworks. We just use them there. Next question. For example, I have 10 nodes Cassandra cluster and it's okay for normal load, but for more load it needs to scale out to 20 nodes. Right. How to scale back to 10 nodes after Cassandra load is back normal, or CPU load per Cassandra node is low? Okay. So the question is essentially, how do you scale certain frameworks within the DCOS? And so there, the question is really what kind of application or service you're dealing with. So if you have, let's take a very, very simple case of a web server like Nginx. So you would either through the UI or through the command line interface say, okay, launch that this Docker image, and then you have these instances here where you explicitly say how many instances of this application you want to have. And if you say one, well then one Docker image is pulled and one container is started. If you say 10, then you will get 10. And you can also have certain restrictions. So you could say only launch them on certain certain IPs or IP addresses or whatever. In case of the framework, it's a bit more complicated, but at the end of the day, for the user, it's the same kind of easiness of use, but it's you don't explicitly do it like I've shown here. Okay. If anything was unclear, if you want more details or whatever, happy to follow up either via Twitter or via email. I certainly take it that's a lot of information for one day. It's really mainly about getting this idea that you can very easily install and launch and scale and in an elastic way use these different big data frameworks together or along with stateless applications such as web servers and so on. How do I run my Marathon task on every Mesos slave? Where slave might be added later, so I don't know how many instances to set in Marathon. Okay, so there's that concept of task, application, and slave or agent as the new terminology is. In Mesos, you're dealing with tasks, right? So if we look at Mesos UI, still there. It's a bit hidden. We actually don't really want to encourage people to go there, but it's there. Then you will see all the different tasks. So Kafka framework itself, broker in a separate task. So that's the Mesos low-level interface. Certain frameworks like Spark, they might launch a couple of tasks, Mesos tasks, for one job, for example, for one Spark job. But in general, task in our context is really a Mesos-specific thing. In Marathon, the unit of deployment is essentially an application, an app. You can group these apps. Now, in the case of these big data frameworks, services like Cassandra, Kafka, Spark, and so on, this is happening under the hood. So you're not manually launching Kafka or whatever. You just say DCS package install Kafka, and then DCS knows what it needs to do and actually represents this known certified service or framework here in the services tab. So a task might run on many different Mesos agents. So if you say, for example, 10, and you look at the overall utilization, in this case, you see this this node here, 10.00.18, has a bit higher utilization than the others. But that's really up to Mesos, right? Mesos will based on the utilization and other information, place these tasks. In Marathon, you can, in addition to that, have placement constraints and essentially say, for example, only launch that application on the public node because you want to give people access to that, and on a private node, people can't connect to that through the web browser. Then it really depends on does it make sense to have multiple copies there. If you have stateless services or applications, then that's typically not an issue. If you have stateful, so any kind of databases and so on, then you would typically need something in addition, for example, EMC code Rexray or Flocker or whatever that manages the state for you. We're working on that, and pretty soon that would be available through Marathon natively as well to deal with these stateful services. But that's essentially the rundown. So you don't have to know in advance. You just make the cluster bigger. So you add, let's say, a new, if you're in a public cloud environment, you create a new instance, a new VM or whatever, and make that part of the Mesos cluster. Then Mesos sees, oh, I've got, I don't know, 5 more CPU shares and 10 gigs of RAM more available, so I have another place to launch that. But all of that is hidden away from you, from the end user, by the combination of Mesos as the distributed kernel and things like Marathon or whatever that shield you from that. You just need to say, okay, I want to have that much resources, or I need that many resources to run. If you don't have enough resources, then Mesos can't launch that. It will say, okay, I'm sorry, I can't launch that. I don't have enough resources available. So you don't have to know that in advance. That's the beauty of it. But you need to make sure that you have sufficient resources to launch that. And many issues I've seen on Stack Overflow and Slack and so on are exactly around that issue. Not having enough resources in the cluster available so that each of these different things can be serviced. I thank you, and as I said, happy to follow up via email or Twitter, and handing back. Thank you very much.